I'm Jon Pearce. Some of you guys know me. I'm Jon WB2MNF, and I'm part of the balloon team that also includes Mike, KG4JYA, and Doug, KD2VQA. We have been working tirelessly on this thing for about 3 months or so, and we really wanted to launch a balloon today. And what we were hoping you would see is this balloon going up, and the reason you're not seeing it is because Joe's on the beach, okay? And when the president is in Delaware, we get temporary flight restrictions, and we can't launch drones, and we can't launch balloons, and we can't do anything else. This is about the 4th time that the president has stymied a perfectly beautiful day for a balloon launch, we're going to have to find alternate places we can launch this thing from, which is all the way down in the shore or all the way up on the, McGuire Air Force Base would work. I don't think we can get there. Normally, the last couple of times, I'll tell you, we were able to launch over at the clubhouse, which is right over there. That's a great place to do it. We were hoping to do it right from the fairgrounds today. Nope, can't do that. There's a big KC-135 flying overhead that probably would drop a bomb on us if we launched a balloon today. So we've got to wait until the president decides he's not going to go. He's going to stay in the White House for a weekend, and then we can go launch balloons again. That's why we are not launching balloons today, unfortunately. So, we started this project because one of our club members is a school board member in the district in which Woodruff Middle School is. And I see I already misspelled STEM, sorry, Angela. And which Angela, now KE2DRJ, is a middle school teacher. Was not a ham radio operator when this started, went through our licensing class and became one, so now we've got a middle school teacher with a ham license who's going to be working with the STEM club. And what we were challenged to come up with something that would be interesting to middle school kids that had something to do with radio. The best opportunity there would be the talk to an astronaut opportunity, which some of the clubs do, but the problem with that is you can put a lot of time and effort into it and maybe not be able to actually do it. And so the second thing that we could do is launch a balloon with an amateur radio transmitter, and if it's successful, it goes up and it flies around the world, and you can track the thing, and it gives you ongoing opportunities to be involved with the stuff, and it also has beaucoup learning opportunities. You can learn about balloons and helium and radio and whisper and data communications. And what I'm kind of hoping is the kids will come out of this understanding what radio telemetry is. And if they come out of that knowing what radio telemetry is, you got an education deliverable that they can actually do something with. So that's what kind of got us into ballooning. And then when Mike and Doug and I started talking about it, we realized we got to figure this out ourselves before we go actually try and launch one with a school. So we've been working on that for the last probably 3 months. We did 2 what I'll call suborbital test flights that I'll tell you about, which basically we knew we're not going to go up and fly around the world, but we wanted to kind of take the SpaceX approach, a planned failure, but learning from it. Okay, and we did a couple of them, and then we launched one a couple of weeks ago that we hope we're going to go up and go around the world, and it didn't. And so I'll tell you what happened on that one as well. So this is the configuration of the balloon. All right, you're going to have a balloon up top, and we've got a couple of different kind of balloons. I'll tell you about that. And then hanging from that is a half wavelength of wire, okay, which basically at the top half of a 20-meter dipole, okay? And then the radio, which we've got a couple of sitting on the table, you can come look at them when we're done, is hanging from that, and then down below that is another half wavelength of 20-meter dipole. We're also starting to work on 10 meters. Mike got one of the radios working on 10 meters, and we're planning on trying that as well. So that's the configuration of what the balloon looks like. Okay, and I'll tell you about each of the components of it as we get into it. So there's a couple of different types of balloons. The one that we're working with now is this Orbs Clear Pico balloon. These are, you can see, they're about $11 a pop. They're party balloons. We haven't launched one of these exact balloons yet. We actually got the wrong ones by mistake. We got the silvered mylar balloons. These look like they're a little bit stronger and a little bit lighter, right? And so we're hoping this will work just a little bit better than what we were doing. And there are people who've flown these things around the world, so we know that there's precedent for it. The other balloon that we got, which we got before we really knew that these things existed, are these SBS scientific balloons that are specifically made to be super pressure balloons for this kind of stuff. We got two of these things. You saw how much the Orbs balloons cost. These are $175 a pop if you're a ham radio club. They're $200 if you're not a ham radio club. They're $150 if you're a school. So we got two of these things. They probably work a little bit better, but they're, you know, $175 versus 11. So we're kind of saving these for the really big events. The next thing is the tracker, the radio that we hang from this. So this has basically got to be a little computer. It's got to be a 10-meter whisper transmitter. We're using the wide area propagation, signal propagation method. Hey, who's familiar with whisper? Who's heard anything about it? Okay, a couple of people are and a couple of people haven't. Whisper is made for propagation reporting. It's usually terrestrial propagation reporting. There's beacons all over the world. People will have whisper transmitters of varying signal strength on different bands. And there are receivers all over the place that pick up whisper transmissions and then sort them out and put them on maps so you basically can tell whether 10 meters is open because you got a station in Germany that's picking it up or a station in Japan that's picking it up or stuff like that. They're 2-minute long transmissions sending very, very little data. They're basically sending a call sign. They're sending a grid square. What else are they? What else is in the base one, Mike? And the power. Okay, so you got a 2-minute transmission that's sending just that. But it's so robust that we've been running 20 milliwatts over there with an antenna that's staying there on the ground and getting it picked up 4,000 or 5,000 miles away. Okay, it's that robust, and there's a whole network of these things all over the world. And so if we put a balloon up, somebody's going to pick it up someplace, and then we're going to be able to figure out where the thing is. So to do that, you need a transmitter, you need a computer, you need a GPS module. All right, and there's a couple of different configurations of that. The one that we really like a lot uses a Raspberry Pi Pico. Okay, this thing is a brand new microcontroller that the Raspberry Pi guys put out. You can buy it from Adafruit for about $5, and it's basically a microcontroller that you program in Python. And you take that and you solder it onto this board that you order from China based on a spec that you download the files and send them up to the website, and you get these things. They're about $6 a piece. We ordered 10 of them the last time, and you literally solder the pins that you lay it up against the Pico, and you solder pin for pin halfway down either side. So that soldering job looks kind of like that. You can see on the outside. This is the torpedo board. This is the Pico, and you're just soldering pin for pin. Okay, and that's what you got to do to assemble the thing. So it's really sweet. So for $11, you've got a really nice whisper transmitter that pulls very little power. And so we put it together in a configuration that kind of looks like that. That was the first one we flew. We were using batteries with it instead of solar cells for a reason that I'll explain in a couple of minutes. But we basically took a soda straw and we mounted the Pico transmitter on. You can see there's this USB cable. Obviously, we use that for programming. We don't fly with that. Okay. And then the soda straw is vertical. The dipole runs right through the soda straw, and that's what holds the thing vertically. And then we use string going from the radio all the way up to the balloon for strain relief. So we're not using the number 32 wire that we're making the antenna out of, and it's a little bit stronger. There's a GPS. You basically solder the antenna onto two different pads on the little board. You solder the power onto the two more pads, and this blue wire sticking out of it is the GPS antenna. So it's pretty easy to put together. The antenna wire that you usually use with this stuff is number 32 wire, which is really, really difficult to work with. We actually started with number 36 wire, and we kept breaking the stuff. but you want something that's light. And then one of the club members came over and said his sons work for a company that does mil-spec wire. Okay, the stuff that's literally used in F-16s. Okay, and this is Teflon-coated silver wire. Okay, and he gave us 2 rolls of this stuff. It's about $4,000 worth of wire. Okay, we got 2 rolls of this stuff, and we got thousands of feet of it. So we can make as many antennas as we want to out of this stuff. And it's really strong because it's Teflon coated and it's silver, so it really connects electricity real well. So we got the best damn antennas that anybody can fly up there. Okay, so that's one of the transmitters that we're working with. This other one is this is made by where's Zactec made? Do you remember? It's not made in the U.S. Sweden. There's some place like that. And this thing is largely assembled. The main thing that has to get soldered onto it is these 2 supercapacitors, and that's the difference between the other design and this design. Is you got these 2 big supercapacitors there, and the supercapacitors are there because your solar cells aren't always going to be in sunlight. They might be swinging around or something like that, or going through a cloud. And you'd like to be able to power the computer and the radio when that's happening. So the supercapacitors will hold a charge for about a half a minute or so. Yeah, about a half a minute. So if the solar cells aren't particularly lighted, you won't lose your radio signal. And you can see the solar cells mount on the side of that thing, and it's we did fly one of them. We flew it last time, and it seems to work well. The telemetry actually on the Pico is a little bit better. We get more data out of that one than we do out of this. But the Pico was $5 for the Pi plus $6 for the add-on, and this thing's about $50. So these things are a little bit more expensive. Then there's one we haven't flown yet that's also about $50, and it's got GPIO programmable pins and I2C devices, so we can actually hang additional sensors off of it if we wanted to, if we can handle the weight, because the weight is always the big thing. Okay. The telemetry format is a standard Whisper telemetry. It's giving you a 4-digit grid square and gross altitude info. Mike's nodding. He knows this stuff a lot better than I do, so. Okay, well, and then there's an additional packet that's added that's sent. So you got a 2-minute normal Whisper packet, and then a 2-minute additional packet that's got a spoofed call sign. I won't go into that, but they're basically using other fields in a Whisper packet for non-Whisper type data. And what that's doing is giving the additional 2 grid square digits. So instead of FM29, it's FM29JR, which gives us a lot more granularity as to where the transmitter is. We get altitude detail. We can also get power and temperature and stuff like that out of it. So we're basically slightly bastardizing the Whisper format to get more telemetry than Whisper is designed to send. And then on the ground, when we pick these things up, that stuff all gets assembled by Sam in software and comes out on some graphs that I'll show you before. Yeah.
Typically, how long would these balloons be within the 6-digit grid square?
Depends on the surface winds. So. So the one that we launched, the one that we launched a couple of weeks ago, was 2 weeks ago Saturday. And that thing floated around in the same grid square for hours. The surface winds were all variable. It. Yeah. Damn near. It didn't start flying east for about 2 hours.
It did move out of the 6-digit grid square. It just took a long time.
Yeah.
But it stayed within the 4-digit grid square for almost the entire flight.
Yeah. Yeah. I mean, it depends on the wind. It depends.
Once it gets up to about 40,000 and it catches a current, then you're going to start to see it.
Yeah. And that's what happened. That's what happened. So it all depends on how strong the wind is. And at that point, the winds at 3,000 miles, surface winds were coming out of the north. 3,000 feet were coming out of the south. 6,000 feet were coming out of the east. 9,000 feet were coming out of the west. So they were just kind of blowing all around kind of South Jersey and didn't really move anywhere. As Doug said, it kind of went straight up until it got to about 25,000 feet when it started getting into prevailing winds, and then it started going east, which is where the prevailing winds were at that time. But when you look at the winds, and if I have a graph of this, I'll show you. There's a website called windy.com, which is really helping us a lot, and it shows you where the wind is blowing. And the wind ain't necessarily always blowing to the east. It can be blowing anywhere.
Yeah, not want to get ahead in your presentation, but some of the tools that we use to track the balloon could actually project where it's going to be in a given time.
Yeah, and I got a slide for that, so I will show that. So this, we don't control anything. We let go of the balloon, and God controls it from there on.
Where it equalizes,
Well, that's it. Obviously, it's a function of the atmospheric density.
Yes.
It's also
Yeah.
a function of the size of the balloon. As you go up, the pressure drops, things are going to get larger.
That's right. That's right.
It's going to reach equilibrium.
It'll or burst.
Payload and a certain amount, we aim for about 5 grams of lift, additional
Yeah.
in there. And if we get about 5 grams of additional lift with the payload weighs, I forget how many grams,
About 20 grams.
and the balloon, that's not our regular balloon, that's one that we use to,
Yeah. Yeah.
46-gram balloon, we should get somewhere between 40 and 45 grams.
Yeah, and I've got slides on a lot of that. But yeah, it basically will rise to the point where the density of the balloon is equal to the density of the air, and that's around 40,000 feet, give or take. So, depending on the size of the balloon, also depends on whether you're using helium or hydrogen. Okay, and I'll get into that. I'll get into that too. I'm going to skip this one because that's too esoteric. So this is windy.com, and this is basically showing you one of the planning tools that we've got. So you can't see the little arrows on this thing, but there's little arrows that are showing where the pressure levels are and where the wind is blowing at any particular point. And this is on surface, but we can also raise the altitude up to 30,000 feet or something like that. And that's how we found that, you know, at surface, the winds were blowing that way, and at 3,000 feet, they're blowing that way, and at 6,000 feet, they're blowing that way, and at 9,000 feet, they're blowing that way. And that's why the thing kind of went around in a little circle before it really got up. So that's one of the things that we use. There's a website called WhisperNet, and this is basically the network of whisper reporting stations around the world that are showing the reports from a particular transmitter. And this is kind of the raw data. When we see a broadcast on WhisperNet, we know that at least the first of the 2 whisper packets has been picked up, so we know that the transmitter's working. That's the first thing we're looking at. So this is W2MMD-1. This is from 9/5. So this is from the 5th. There's a couple. Yeah, so this thing, the transmitter's hanging in Mike's backyard, and it's getting picked up from 4,000 miles away, I think. Right, running 20 milliwatts, okay, on solar cells, right? So this is basically the raw data coming down, and it's the first thing we look for when we launch one, and that tells us that the transmitter is working, okay? One of the tools we really like is this thing called SondHub. This basically shows, obviously, a map of where the balloons are, most notably where our balloons are, and you can get additional information about them if you click on it. And this is what Doug was talking about earlier. This is a particular balloon that I think it's out in Ohio that I found when I was putting this together. And so you click on it. If you click on the balloon, you get detail on the balloon. So this thing was all the way up at 16,000 feet, 16 degrees Celsius, running the WD8 Sky Tracker module. That's the kind of transmitter it was into. And if I click on float, it does a prediction of where it's going to fly based on the winds at the altitude altitude that it's at. So in this case, this thing was supposed to go swirling around here, fly around here, and then it would go there. And each of these is a different predicted path that it can take based on where the winds are, which is really pretty cool. And what was fun to look at when we launched the last one is, as I said, at each level, the winds were different. And so the projections of where the balloon was going to go changed radically as the thing went up. Because, you know, if you're at 3,000 feet, it thinks you're going to stay at 3,000 feet. The winds are blowing west, so it's going to predict it west. Then, you know, a half hour later, the winds are blowing a different direction. And so we got totally different prediction. We had no idea where the damn thing was going to go until it got up to an equilibrium altitude. So, but that's one of the really cooler tools that we think we can use. And again, I'm projecting this out to the school where Angela's students are going to be looking at this stuff. And, you know, so where's your balloon going to go? You know, anything we can do to create interest in it. And then this I zoomed out to show all the balloons, and there's an awful lot of balloons out there. You can see they're being launched all over the place. There was one experiment where a guy got funding to go to go to Antarctica and launch balloons down there. And you don't have prevailing winds in Antarctica. So the thing just flew around Antarctica for a while, which was really pretty cool. And they did the whole research paper on that, you know, including like bursting pressure and stuff, which is really, really useful for us to read. What's this? Oh, and the other thing you can look at is the telemetry. Okay, so this is just an example from the page that I picked up. This isn't one of our balloons. But this is altitude, this is temperature in degrees centigrade, this is voltage, this is speed. Okay. So we can get the actual graphs of the telemetry coming down, not just the balloon position. Okay, so there's some of the tools that we've got. What else do you need that I haven't talked about? Helium. So you can either use helium or you can use hydrogen. Hydrogen is a more effective gas and it's much cheaper. What's the problem with hydrogen? It's explosive. Okay, where are we going to be taking this? Into a school. Okay, how do you think that would have gone over? Probably wouldn't fly, right? Okay, so we decided not to use hydrogen. But fortunately, helium, we got the tank, the regulator, and a tank of helium donated to us because one of the guys works for Airgas, and they were willing to make an in-kind contribution to the not-for-profit foundation, that is the Gloucester County Amateur Radio Foundation, and also to the school. Okay, and so we got a really nice tank of helium, and we can get filled at employee discount prices, which is far, far below what helium costs on the retail market. Plus, this is not party balloon helium, which is only 80% helium. This is pure helium. So it's got 25% more lift than party balloon helium does. This is the real stuff, okay? So we got the helium down. The important thing that we've got to do is we got to have lift and weight right. So we basically weigh everything. We weigh the trackers, we weigh the solar cells, this is weighing the antenna. And we use a gram scale for everything. This is the antenna that weighs 3.3 grams, all right? And that matters, okay, because we're down to the 1/10 of a gram on some of this stuff. So what we do is we calculate the weight of the payload, and then we have to figure out how much gas to put in the balloon to lift the payload plus 5 grams. The recommendations are somewhere between 5 and 8 grams of net lift to go up. And we launched one a couple of weeks ago. Doug wanted to launch it with 5 grams of lift. I was holding my breath because that sucker was going right towards the VHF tower down at the clubhouse when we launched it, but it did lift above it, and I was able to breathe without needing CPR from Doug. So now we know that 5 grams of lift will lift these things. And so what we do basically is calculate the weight of the payload, and then you can see this is Doug weighing, and then we'll hook it up to a weight. Okay, and we'll put gas in until we get enough lift that the gram scale is weighing less than the weight. So if we got a 100-gram weight on there and we needed 20 grams worth of lift, we put in gas until that 100-gram weight weighs 80 grams. All right, that's how you do that kind of stuff. So basically, he's checking the lift with the helium tank there. Mike's checking it out to make sure he does it right, and I'm of course taking pictures because that's all I can do. And we inflate it to that point, and then we stop. And you can see that's probably about what that's about as full as we get, right?
That's it. When it's starting to go up, it looks like the balloon is compressed, like it doesn't have much air in it. And as you said, as it goes up, the balloon's going to
Yeah. Right. Yeah, so it kind of looks like that. It doesn't look like that. That's got 150 grams of lift. We filled the whole thing full of helium. Lift a chair off the table. And then this was doing the party balloon. All right, that we just wanted to see what happened when we filled a balloon up. That's the first balloon we filled up with helium. So we did a couple of tests with test flights. Like I said, we used the Mylon party balloon. Basically, used that balloon. We used the Pico tracker, the cheap one with the $11 one. We used the LiPo battery on it because they were cheaper than solar cells, and we hadn't yet figured out how to use the solar cells. And we knew it was going to be a short duration flight. This is one of our planned figure out how to do it. We'd never launched one before. We got to get the logistics of it down. And we knew one of three things was going to happen. The balloon was going to pop, the battery was going to run down, or the balloon was going to freeze. One of those three things was going to happen. Okay, so the first one we did was with a party balloon, and we decided that we would try, because the gas is going to expand, we left the soda straw inflator in the opening, and we put some fuzz from a mop in the clubhouse up there to basically allow that if the balloon expanded, the gas could come out the port and wouldn't pop the balloon. And we thought, maybe that'll work. Okay? Nobody had ever tried that before we decided we were going to try it. We put a 2,200 milliampere hour battery on that, and our goal was to get to 1,000 feet. That's what we thought was, what? 10,000 feet, sorry. So this is basically what this thing looks like. Doug basically took his fishing pole out there, and we ran a loop of monofilament line from the fishing pole out to the balloon and then back. So it's looped over the radio or one of the connectors on the balloon, so we could reel the balloon out and see which way it was blowing, and then also get the antenna so it's vertical, so we could check the transmitter, but we could also bring it back in if we needed to change something. And then when we launch it, we just let go of the other piece of monofilament, goes up and back, and the balloon just keeps on going up. So that's Doug is holding the fishing pole. Angela was holding the balloon, and see, I think this is a video. Yeah, there you go. So we had about 8 grams of lift on that, I think, didn't we? So that thing went pretty well straight up. And it disappeared, and it continued on going up, and we got telemetry from it immediately because we were running off a battery. One of the things we might not get is we're running off solar cells. We might not get telemetry the whole time because those solar cells may not have enough daylight on them. So we got to launch late enough in the day so the sun's high enough in the day so it's going to be shining on the solar cells. Okay, otherwise we don't get any telemetry until the thing, till like 10 o'clock in the morning, and we don't like that. That scares us. So this thing went up to 22,000 feet, and you can see, you probably can't read this, but that's flying over Lakeland Air Force Base, which kind of made it really interesting. We're wondering if that's going to get shot down. And that was the path that it took. It really kind of went up and kind of went straight northeast, and ended up, I'll show you where it ended up in just a second. But this is the telemetry that we got. You can see it's going slightly up and slowly down. And what we figured from that is that it went up high enough that, because of that vent that we had in it, that it got compressed to the extent that it blew out so much helium that it no longer could lift the balloon. Okay, it couldn't lift the payload up. And then it started coming down because it didn't come straight down. So it didn't burst, but it didn't have enough lift. So it just kind of slowly went up and slowly went down, and it landed. Then the next bet was, is it going to make it into international waters or not? And it did make it slightly into international waters, which has no particular significance other than the fact that once it had hit 10,000 feet, we needed another goal. Okay, so that's the first flight. The second flight, we sealed the bottom of it. That's really the only difference. Okay, and it went up and it went southwest. And what happened on that one, strangely enough, is we didn't get any telemetry for about an hour. I think, in fact, Mike actually went home because we thought we'd lost it, you know, and then all of a sudden we started getting, Doug and I were still at the clubhouse, we started getting telemetry on it, and then we started getting locations for it. And that's another one where it just kind of floated around and floated around. And so you can see from this one that, I'm getting ahead of myself, I hadn't advanced to that slide yet. Okay, so this is altitude. We're going up to about 29,000 feet. We're watching it go up. We're also watching the temperature go down. Because what happens to a lithium battery when you get to freezing point? Okay, we knew that was going to happen at some point. What we didn't know, again, is whether the balloon would pop, the battery would run down, or whether it would freeze. If it never got high enough to freeze, then the battery might run down, okay? But we get 0 degrees, battery voltage drops, telemetry stopped, okay? So we don't know how high that thing eventually went. And I don't have a picture of where it landed. I guess I do have a picture of it. Yeah, it landed. It landed on the field somewhere down here. Like, I don't know, 5-6 hours later, when the battery unfroze, we saw the altitude is 0, and here's where it is. And unfortunately, it's within a 6-digit grid square. That's the level of granularity we've got for the geography for it. And that's, I think, a 2 by 3 kilometer square. So Angela decided to go see if she could find it. You know, she and Craig drove down there, and they drove all over the place. This is, I think it was one of the red balloons, wasn't it, Doug? Didn't we fly? So it's this big red balloon. Yeah.
100 meters.
What's that?
6 digits is 100 meters. 6-digit grid square is about 100 meters.
100 meters? Yeah. I see, saying a 6-digit grid square is about 100 square meters. Yeah. Okay. Yeah. Well, anyway, it's sitting somewhere, and
It's in a cornfield somewhere.
it's in a cornfield. They couldn't find it.
All that was down.
All right. So the third one, actually the fourth one, the third one we launched was a one of the cheap balloons, and we didn't have the solar cells set up right, and we didn't test it right. And as soon as we launched it, we lost telemetry. We just didn't know what happened to it. So we're ignoring that one, except that we're not going to make that mistake again. The fourth one was one of the Zactec trackers. And this one we were launching with solar cells. We're hoping this guy's going up and it's going to fly around. Okay, so 32-inch silver balloon, the Zactec trackers, and with the supercapacitors, 2 5-volt solar cells, and we're hoping, this is not a test flight, we're hoping this thing actually flies. So we had this brilliant suggestion, that I think this was Doug's idea, right? Or Mike's idea. Everything here is collective. We have a Discord site that is constantly updated with all the stuff we're doing. So anyhow, what we wanted to do is we wanted to get the whole dipole lifted up so we could check the tracker before we actually let go of the balloon. The problem is that the weight of the fishing line that we're using to hold it down we don't have enough lift to lift that and everything else. So what we did is we took that balloon, which has got like 100 grams of lift because it's all full of helium, and we used that to pull the other balloon up. And we tied a string to that so then we could release the silver balloon and hold on to the red one. But in the meantime, we got the whole dipole vertically, off of the ground. And so that let us, check the transmitter. This thing's hanging out there for about 20 minutes while Mike's in the clubhouse watching to see, WhisperNet, to see whether we're getting transmissions. We could check, we made sure we're getting telemetry, and then we let go of the balloon. Okay. So this was the last transmission that we got. And it's up at 34,645 feet. After it had meandered around, this is the one that literally went around in a circle before it went up. Finally started blowing east. We launched at 11 o'clock in the morning. The last transmission came at 3:18 in the afternoon. And what we thought happened there, this is Mike decided that solar cells are like this. The sun angle is low. You really have to have the sun aimed at a solar cell because you're going to get any voltage off of it. And so we decided that the sun angle had dropped to be too low for the solar cells to be illuminated, and that's why the transmission stopped. And at that point, we said, go home, go to sleep, get up the next morning at about 10 o'clock in the morning, go check and see if you've got telemetry. And when we did that, we got no telemetry, and we've never gotten any telemetry. So on that one, two things could have happened. One is we had a catastrophic balloon failure that happened overnight while we were, at night, solar cells aren't illuminated. We never get telemetry at night. We're only going to get telemetry during the day. The balloon might have failed, might have gone in, or we could have also had a radio failure, and that balloon might still be up there. It's just not transmitting. But Mike did all the work on the radio. He's confident that we did not have radio failure. It's not Mike's fault. It's not Mike's fault. So we just, and the problem is we don't know what failed, and so we don't know what to fix. And there's a lot of things that just can be bad luck. And so I think at this point we've decided it was bad luck, and the next time we're going to launch the same thing over and over again. The only thing we're changing next time is we're using the clear balloons instead of the silver balloons, and we're going to heat seal the balloon instead of putting tape over it to seal it, because we were taping the inflator point shut with Kapton tape, and that might have leaked. So now we've got a heat sealer, and we're going to seal that. So the next one we're going to try and do is 10-meter telemetry. Mike's got one of these things configured for 10 meters instead of 20 meters, which means the antenna is half as long, which means it weighs half as much. So we've gained about 1.5 grams back of lift that we don't have to create, which means helium that we don't have to put in the balloon, which gives us more room to expand when we get up into the upper atmosphere and less chance of bursting it. Okay, and Mike's had this thing running in his backyard, and we've gotten telemetry from all over the world. Seems like 10 meters is open enough that we can do this. So we're going to try that. We also want to do a demo flight for the STEM students, not the SEM students, John. I can spell, Angela. And we got to figure out when we want to do that. But we basically want to do that down at the school sometime to generate interest in the STEM course, which is going to start on the 23rd, something like that. So the project for them is we want to get them doing stuff really quick. So we want them actually to do the soldering on these things. So the first week, we're just going to do an intro. The second week, we're going to teach them to solder. And we got a bunch of little soldering kits that we're evaluating. We got to go through the soldering kits and decide which ones we want to use too, guys. Maybe we do that on Saturday. So we're going to teach them to solder the second week. And then the third week, we want to have them actually soldering together whichever of these kits we decide to get. And then launch them at some point thereafter. Because, some kids can be soldering, some kids can be cutting the antenna. And then there's ongoing experimentation and stuff like that. Yeah.